Good afternoon to all of you. Good afternoon, Simran. Good afternoon, Salesh. Good afternoon, Vandana, Nimishka, and Rishita. I hope you all are well. I hope you all can hear me clearly and see my screen too. So let's go ahead with today's class. Our exams are coming near, so whatever we will cover up till today's lecture, we will keep for the exam. Today I am going to start with 8th chapter. Typically we keep 8th chapter complete for the exam, but of course since we are starting today we won't be able to complete it, and therefore whatever we will cover today we will keep that for the exam, and the rest we will keep for end semester. As I said, as I have earlier stated, we are not asking anything which is not covered in the lecture videos, so you can focus on them. That should be sufficient for your exam, including problems which have been solved when we did problem solving in the class, and also do focus on assignment problems. Thank you, Nimishka and Rishita. So once again, very good morning or very good afternoon to everybody else who have just joined. Let's start with this lecture. Here we are going to talk about combination tones. Remember, we started with psychoacoustics. We are continuing in that section of acoustic studies, that how do we perceive sound. And we have seen various aspects of this perception of sound. We have seen loudness, we have seen intensity, we have seen pitch, quality, etc. etc. Now we are going to talk about, if there are more than one tones present, then how do we feel or how do we perceive the sound? And that is all that we are going to discuss in this chapter, that is combination tones. We are going to start with the simplest possible case. We are going to take two pure tones of the same frequency. So we are going to take two pure tones of the same frequency. That's the simplest possible case to begin with. And then we will look how they superimpose on each other to give you the final answer. And then you will take two pure tones of slightly different frequencies, and then which leads to beats and critical bands. Which leads to beats and how they are related to critical bands, that we will see uh, soon. And then we are going to talk about two tones which are separated by large frequencies. So we are going to start with two pure tones of same frequency, two pure tones of slightly different frequencies, and two pure tones of much different frequencies. And remember, when I'm talking about pure tones here, I am talking about pure sine waves. So going ahead, first of all, let's take the first case, two pure tones of the same frequencies. Such tones are called combination tones. In the later part of the chapter, we are going to talk about complex tones and chords, but that is not in today's lecture. That is the lecture that we will have later. So what happens if you have two pure tones of the same frequencies? So as we are all familiar, two sine waves arriving at the same point, same instance, will undergo what is called as linear superposition. What is linear superposition? Recall your earlier knowledge of adding two waves. Many of the things that we will discuss today you have already done in the lower classes, so they won't be much challenging. So linear superposition is a vector sum of the two amplitudes. So if you have two amplitudes, then they simply add up vectorially. Here I have two waves. When they appear this way, that is crest with crest, and trough with trough, then we say that they are in phase. When they are in phase, they simply add up and the final amplitude is A plus B. If they meet this way, crest with trough and trough with crest, then they are out of phase and they simply add up as A minus B. But the resultant is also a pure sine wave. Remember, pure tone. Whenever you have two pure tones of the same frequency, you have done this long derivation in your 11th or 12th, wherever class, where you have found that if you if they are in phase they will add up, if they are out of phase they will, and if they are having some other phase relationship, neither in phase nor out of phase, then it becomes little complicated, but still the linear superposition would still give you a third frequency or the third, sorry, a third wave of the same frequency, but a different amplitude and different resulting phase. So here I have one wave of larger amplitude, I have another wave of smaller amplitude, but the phase difference is arbitrary. Remember, their frequencies are same. Whatever is the frequency of this, same is the frequency of this, but their phase relationship is arbitrary. So they are neither in phase nor out of phase, some phase relationship. You know that SHM can be seen as a projection of a circular motion. So this is the phasor diagram. For example, this SHM can be a projection of this larger rotation or larger circular motion of larger radius. This small amplitude SHM can be a projection of circular motion of smaller radius. If I take this x-axis as a reference line, then this may have a phase phi 1 or phi A. This may have a phase phi, complete phase as phi B. And if you superpose the two, then the resultant is generally given by this, where A is the amplitude of the first wave, B is the amplitude of the second wave, and resultant amplitude is given by root of A square plus B square plus 2AB cos delta phi, where delta phi is the phase difference between the two waves, that is this phase difference from here to here. That is, if there are two peaks, how much they differ from each other in phase. Remember, just to recall, if the two peaks are separated by a wavelength, then the phase difference is 2 pi. So phase difference per unit length of the wave is 2 pi by lambda. So if there are any other part different delta x, then the phase difference delta phi would be 2 pi by lambda into delta x. So do remember that you have already studied. So this becomes the resultant amplitude, and the resultant phase of the resulting sine wave is given by this, which is a bit complex looking, but this derivation also you have done in your lower classes. So what is the takeaway? The takeaway is, if you have a pure tone, two pure tones of same frequency, if they are in phase, they will appear louder, but frequency is same. If they are out of phase, they appear very small, very feeble, very dull, very less intense sound. But again, same frequency. If they have any phase, remember when they are in phase difference is 0. When they are out of phase difference is pi. When they have any other phase relationship, then the amplitude can be predicted by this equation, and accordingly intensity will vary, but still frequency remains the same. Remember, intensity is proportional to the square of the amplitude. So at any point you can calculate frequency, sorry, intensity if you know amplitude. We have done that equation in our revision, first two revision lectures. So do recall that. But important point here, I would like to say that if you have two tones of same frequency, your resulting tone also has the same frequency, which will not be the case as we take our discussion forward. Now I'm going to introduce two pure tones of different frequencies, and right now I'll keep the difference very small. So what happens when you have two pure tones of very small difference? Can anyone think about it? You all know this. In fact, we have done this in the revision as well. You get a phenomena which is called as beats. When two pure sine waves of slightly, or two pure sound waves, when I'm saying pure tone is pure sine wave, pure sine fluctuations. So if you have two sine waves of having pure frequencies, but they're very close to each other, and if they are sounded together, what you get is a phenomena of beats. You know that the beat frequency is the difference of the two frequencies which are sounded together. Yes, Pranav, thank you. Two difference of the two frequencies. So if one is 100 hertz, other one is 102 hertz, then you will get 2 hertz at the beat frequency. And the sound frequency, the sound at which the beats occur, is f1 plus f2 divided by 2. So for example, if it's 100 and 102 hertz, then the sound frequency will be 101 hertz, while beat frequency will be 2 hertz. But let's say we repeat the experiment at 500 and 502 hertz, then the sound frequency will be 501 hertz, but the beat frequency would still be 2 hertz. So that's what you get. So if you hear two tones, but let's take this discussion forward because this is very important in whatever context we have developed so far in these lectures. First of all, how would it look graphically? So graphically, if you plot beats with time, then they generally look somewhat like this. If you have done bit of electronics here and there, then you must have come across term called as amplitude modulation. This is exactly that, amplitude modulation. So do check that if you wish to. Amplitude modulation is nothing but the addition of two frequencies which are close to each other. Now, these are the positions where amplitude is high, you will hear a high sound. These are the positions where the amplitude is less, you can hear the less sound. Remember, you have already exposed to the tone generator app. If you have two mobile phones, two devices at home, you just have to play the tone generator app on both and sit there and try to listen to the resultant sound. And if it's a quiet environment, maybe in the night, you will be able to clearly hear the beats. You can turn on and off each one of them alternately and figure out how does it sound when just one tone is there, and how does it sound when both the sounded together. So yeah, so this is the maxima, this is minima. The separation, the time separation between two maxima, which is the beat frequency or beat period rather, is 1 over f2 minus f1, where f2 minus f1 or f1 minus f2 is beat frequency, and the sound period, the sound wave period is this, which is sum of the 1 upon sum of the two frequencies divided by 2. That is reciprocal of this figure. So that's how it looks graphically. How would it achieve it experimentally? So classically in the laboratory we used to do this setup. We used to take one or two audio generators or frequency generators or AFG as we call them. We combine them together with the resistance, feed it through a CRO, and on the CRO you can see the patterns, feed it to an amplifier and speaker can give you sound. So both the things were possible in laboratory, but that was the days when the mobile phones were not there. They are fairly versatile device as far as physics studies are concerned. So as I said, you simply use two tone generator apps on two different devices, and that is more or less same as this one. Now taking this forward, And that is the most important part of today's class. The beats, when you are arranging and hearing, then you will find that if you have 100 hertz, if you have 102 hertz, F1 and F2, and if you play them together, your ear would neither listen to 101 hertz nor to 102 hertz. It will not hear both the tones independently. Instead, what it is hearing is beats. A beat tone is a fused tone, it's a mixed tone. It does not have any identity. It does not have the identity of 101. It does not have the identity of, sorry, it does not have the identity of 100 hertz. It does not have identity of 102 hertz, but it's a new tone, it's a new frequency. It has other variations. It's a fused tone. That is the question, that why does it happen? Why, if our ears are presented with two slightly different frequencies, then they, why aren't they heard independently? I mean, otherwise the ear is a remarkable device. If you play two tones at a far difference, ear can hear them clearly. But if they are very close enough, then what ear does is it does not hear it, but it hears a fused tone. So this happens typically because if there are two frequencies which are very close to each other, then they typically fall on single critical band on the basilar membrane, and they activate the hair cells in the same region. Their activation envelope, frequency envelope overtly overlap with each other, and the overall sensation to human brain is not of independent frequencies. Human ear cannot distinguish between them clearly. That is what is called beats. So I have a graph here which looks complicated, but let me simplify. What the graph is doing, it's plotting a frequency f on this axis and the delta f on this axis. For example, I can keep one frequency fixed to study beats. I can keep one frequency fixed at say 100 hertz, which will be my f. Other frequency I can vary from say a frequency lesser than 100, maybe 80 hertz or 60 hertz, to a frequency which is higher than 100, maybe 150 hertz. So I can vary. As I vary the frequency, I will change the difference between the two. So on the on the x-axis, I am plotting the difference of the two frequencies. Remember, when the difference of the two frequencies is zero, that means my two frequencies are identical. That means I'm here in the graph. If my one frequency is fixed, let's say at 100 or f, if the variable frequency is less than delta f, I am on this side. If the variable frequency is high, then delta f will be f2 minus f1 and I am on this side. That is how this graph is there. Now what has been observed is, and remember, now we are going beyond beats. So now what is being observed is something which is very straightforward. If the delta f is less than 10 hertz, and these are general approximate averaged out figure. When you do an experiment, instead of 10 you may get 12 or it may get 8. It depends. So if delta f is less than 10 hertz, what has been observed is generally you won't be able to hear the two tones independently. What you hear is a fused tone, which is beats. Okay, and the beat frequency is delta f. So as from center, from difference 0 as I go on to this side up to a delta f of 10, and I go on to this side up to delta f of 10, then on both sides of 0 I would get clear beats to be heard. Okay, so for example, if one is 100, other one is 95, I will get 5 beats. If the from 95 I change it to 106, I will get 6 beats. So beats are heard. The two tones can't be separated. They fuse into each other beautifully and they sound as a single note. However, what has been observed it that as you keep increasing your frequency difference, then there is a zone of uncertainty between 10 to 15 hertz. Some people, some frequencies, you will hear beats, and some frequencies, the beats will not be clearly audible. But what instead you will get a single rough sound, some sign, some type of roughness in the sound will appear, and the single rough sound will appear. Remember, it's still a fused sound. It's still a single tone. Two tones are not heard still. Okay. Now, after as you increase delta F beyond 15 hertz, what you would realize that the roughness continues. Sound is still muffled, but you will find that the fused tone or a single tone is now diminishing, and what is appearing now are the two independent tones, two independent rough sound, but still it is there's quite a bit of roughness involved in the production of sound. Finally, towards the end, if you increase this difference beyond critical band, say 50 hertz or 60 hertz or 90 hertz, whatever is the critical band at that frequency, if you go beyond that, then roughness will completely disappear and the two tones are heard very independently and clearly. So reason we give to this is that initially when the frequency difference is very less, then only one section or one critical band is undergoing resonance with the sound and the sound is fused. Even when there is a difference greater than 15 hertz, the resonance area on the basilar membrane are separated by some distance, but still they their overlap, their envelopes overlap, and the roughness persists although the fused tone is vanishing. But once once the two regions or two frequencies are so differ from each other that they fall on two different critical bands, then they can be sensed very clearly, independently, and a sweet sound or sweet note or tune sound appears. Roughness will disappear continuously. So this is an experiment, very simple experiment to assess the critical bands in human ear. So I mean, if you want to figure out the critical bands, this is a very simple and beautiful experiment. Can be done with mobile phones, can be done with mobile phone and a set of speakers as well. So keep a note of this when your projects will appear. So going ahead from this point, beats are also heard. Now, very interestingly, earlier what we spoke of was that the sound is mixed and then presented to human ear. So you play your mobile phones and two app generator app, just play them, keep them say 2 feet away and sit there and hear them. That is what we discussed just now. And here what is happening is the two frequencies are first mixed into each other in air and then they are served to human ear. That is the great thing about it. However, the binaural beats are also heard. What are binaural beats? The answer is when the two slightly different frequencies are presented to two ears separately, not together. That means they are not first mixed in air and then presented. No, they are presented separately. So, for example, you connect two headphones to two tone generator apps in two devices. Put one headphone or earphones plug in one ear, put the other one in the other ear, and play the two frequencies independently. So you are feeding the two ears independently. The sound is not mixing first and then going to both the ears. Instead, you are giving some independent frequencies and amplitudes to both the ears. If that happens, still the beats are heard. That's the beautiful thing. The beats are still heard, the maxima and minima would still appear, delta at the frequency f2 minus f1, even if you slightly different frequencies are given. Now look at the beauty. Here, earlier what we said, that on the same basilar membrane in the same critical bands the sound is fusing. But here that is not the case. Your two ears has got two basilar membrane. One basilar membrane you are making it sense only one frequency. The other basilar membrane you are making it sense some other frequency. So here the beats are created in the somewhere in the brain, somewhere in the mind, somewhere where the audio processor is situated. That is taking the clue and creating beats. Although such beats are best heard at a frequency less than 500 hertz and at a sound frequency of around 500. So if you are experimenting with this, see to it that you choose correct frequencies. It's a rotating tone in a sense that if you close your eyes and hear to it, you'll find that the sound is in your brain, the sound direction is changing from left to right and right to left in a circular fashion. That is what is called a rotating tone. It typically happens because of the phase difference between the two. In fact, this is a the common tactics which is used to generate the surround sound movement in theaters and all. So all speakers are fixed in a theater. So how do they create the effect of a vehicle moving from right to left? The answer lies in this kind of experimentation where you delay the phase. So yeah, so that's also called as rotating tone. So that these are called binaural beats. The third is the difference tone. Remember, we started our lecture with two tones which are equal to each other, and then we went to the part where two tones are slightly different but presented together, and then slightly different and presented differently to two ears. Now we are getting into the third example where it is the difference tones which comes in the picture. Now in the difference tones, what happens is we still have two pure tones, two pure sine waves. Two ears are presented to two pure sine waves, but the difference is large. One is a higher frequency, one is lower frequency. The chances of beats are not there. Chances of fused tones is not there. They can be heard independently. But what you would realize that when two tones are sounded together, a lower tone is frequently heard. It is called a difference tone, first identified by Tartini, so it is also called a Tartini tone. And I have done this on this also. I have done experimentation at home with mobile phones and speakers, and you can try working on that. You can play two frequencies, say one frequency at 500, second frequency at 400, and you will find that if you play them together, you will hear 500, you will hear 400, but you will hear a third frequency also, which is f1 minus f2, which is, say, in case of 400 and 500, you will hear the third frequency as 100 hertz, which is a combination tone. So that phenomena also occurs. Now, where does this third frequency come from? So there are lots of explanation available. The third frequencies, I will suggest you to go through it on the net or in the book. So in fact, there are multiple combination tones possible, not just the first difference. For example, there is a combination tone 2F1 minus F2, etc. So you will have different combination of these will appear in human ear. They are very feeble sound. So generally the loudness should be high to hear them with experimentation. So, but of all the combination in our discourse, we will stick to one which is F1 minus F2. I have a demo here which perhaps give us some idea about the Tartini tone or a difference tone. So if you have a phone, keep volume slightly high. Wait. Yeah.
Warning, what you are about to hear cannot be unheard. You will hear two piccolos, which means that it hears the sum of and the difference between two separate frequencies whenever you hear them. These sum tones and difference tones can sometimes be quite faint, but they are always there when you hear two or more notes. I asked my friend Brian Kroc to play the beginning example on a piccolo, because combination tones are easiest to hear with high, loud, and pure sounds. Very often this is done electronically with sine waves, but the closest instrument to doing that sort of thing is a piccolo. I also asked Brian to do an experiment of sorts to see what kinds of combination tones are possible. Listen carefully as Brian plays a steady C natural on one track, and then also listen to how he ascends chromatically on the other track. You should hear a low tone, the difference between the two tracks. Combination tones can only really be heard at moderate to high volumes, so please turn up your volume and hope that anybody that you live with is into learning about psychoacoustics. You might notice that as Brian...
Please listen to this. Please listen to this very carefully and once again. Once they are playing, once he is playing this instrument called piccolo, you are getting another undertone to that sound. I'm just playing it once again and you can check it later as well.
At moderate to high volumes, so please turn up your volume and hope that anybody that you live with is into learning about psychoacoustics. You might notice that as Brian ascends by half step, the combination tone...
So you can check this later on. I'm going to leave the link for this video also in the description to the lecture video. So you can check this as well for your further reference. Okay, so that is the last topic of discussion in this class. In the next class, whenever it will happen, we are going to talk about what happens if there is a complex combination of musics, then what happens to combination tones. Till then, we can stop here. Thank you. I'm going to I'm going to create a Google link, our usual link, and if we have anything to discuss, talk about, we can talk there as well.